Let's now look at the charge on the protons. Protons and electrons have equal and opposite charge. By the convention set by Ben Franklin, electrons have a negative charge and protons have a positive charge. This is where the charge on big objects you can see, come from. Neutrons have no charge, they are neutral. Atoms are electrically neutral, not because they contain no charge, but because they have equal numbers of protons and electrons. So if you add up +5 to -5, you get 0. So the total charge adds up to 0, and we call that neutral. However, if an atom gains electrons, it will have a net negative charge, and we will call it a negative ion. If it loses electrons, then it has a positive charge, and it's called a positive ion. We're not going to get too much into nuclear structure now. That'll be part of the nuclear physics part of this course. But real quickly on this, if you change the number of protons, you're changing the element. If you change the number of neutrons, you're changing the nuclear behavior of the element. The different numbers of electrons enable you to have chemical bonds and molecules and all kinds of other cool stuff. But we'll talk about that later in another unit. To review, like energy and momentum, both linear and angular, charge is neither created nor destroyed, it is conserved. Opposite charges attract, so a positive would attract a negative, and like charges repel, so positive repels positive, negative repels negative. As a result of this, negatively charged electrons are attracted to the positive nucleus, and that's an atom. The neutrons aren't doing anything in that role, but it's the positive protons attracting the negative electrons. Here's a really cool thing. The electron is so much tinier than the proton, 1,800 times roughly. However, the charge on an electron is exactly equal in magnitude to the charge on a proton, and its magnitude, as we've said earlier, is denoted by E. That's just fabulous. If you picture, let's just draw a rough picture. Let's say this is a proton, and you really can't do this, but we'll use it to illustrate it. Here's an electron. This guy is way, way bigger than him, much more massive. However, the charge on this proton, the plus here, plus E, is exactly equal and opposite in sign to the charge on the electron. In older science books, and maybe in some elementary science books that are still out there, you see a picture like this and they tell you, hey, here's the atom. Here's a nucleus. Here's the electrons orbiting around it, just like the planets orbit the sun. Although actually, the planets orbit the sun pretty much in one plane. They don't go all in different ways, but don't worry about that. But if we were to magnify, if somehow we could magically make an atom so that the nucleus, right here, was the size of a baseball, the atom would have a radius of 4 kilometers. In other words, let's say, well, here's a baseball. Here's our nucleus like this, little baseball. The nearest electron wouldn't be right here. It would be 4 kilometers away. And the electrons would be approximately the size of this period right here. So if I've got this nucleus here and I've got electrons, well, I can't really draw 4 kilometers on this page, but that's pretty far away. What does that tell you about atoms? They're mostly empty space. Then since everything, including us, you and me, is made up of atoms, that means everything, including us, is mostly empty space. Here is a more realistic visualization of a helium atom. Now, I say here's what the atom looks like, but in reality, we can't see an atom. There's many reasons for that. It's tiny size, the wavelength of light, etc., but you can't see it. You can't take a picture of it. So we do visualizations, and we try to make them accurately portray what's going on. Here's the nucleus of a helium atom. See, two protons, 2 neutrons. You bury that way deep within here. This box is this little tiny piece here, and then you see this dark area and this light area. Okay, we're going to get to that. But the nucleus is 1,000,000 times smaller than the atom itself. The width of the nucleus is 10 to the minus 7th nanometers, where a nanometer is already 10 to the minus 16th meters. That's really tiny. So we have a magnified view of the nucleus here, and then we have these dark black colors and gray, then a little lighter, then a little lighter still, so lighter that you really can't see it out here. What does that mean? Just as a clue, what haven't we talked about? We have neutrons and protons. What are we missing at the moment? You know that helium has 2 electrons. Well, maybe you don't know, but if we have 2 protons and we have a neutral atom, we need to have 2 electrons to balance off the charge. You don't see electrons here. You don't see an electron over here orbiting or another electron here. And that's because we don't know exactly where they are. We only know a probability of where they are. The darker the shade means that it's more probable that the electrons are found within here. As you get lighter, you have less of a probability of finding the electrons, and then out here it's a little less, and then further away a little less. And for more information on this, we're going to cover that in the Quantum Physics and Atomic Modeling chapter of the AP2 physics class. For now, we're just going to say those 2 electrons are somewhere around that nucleus. We've already shown that electric charges move between objects. Remember the ruler and the bits of paper, and the rubber rod and the fur, etc.? So based on this picture of the atom, we have the nucleus buried way deep within, and then the electrons kind of flitting around somewhere out here. Which of the constituents of the atom look like they could move between other atoms? Would it be the neutrons and protons deeply buried within the atom, or the electrons? I'm kind of leading you to the answer here. Electrons. Electrons are the particles that will move between atoms. They're not bound together as tightly as the protons and the neutrons that are stuck way deep within the atom. The electrons are fundamental particles. At the moment, and this is very key about all of physics, physicists have not found any further structure within the electron. That doesn't mean that they say 100% there is no structure. And as a matter of fact, there's a good deal of research going on, both theoretically and experimentally, to see if there's something inside the electron. Physics is never done. Okay, but let's go and talk about the neutrons and the protons, because we've already found that the neutrons and protons do have something inside them. Quarks. Neutrons and protons are actually made up of elementary particles called quarks. And we're not even going to discuss yet whether quarks have something inside of them yet. At the moment, the theory is quarks are elementary particles just like electrons. Murray Gell-Mann, along with George Zweig, proposed the existence of these particles to help explain the many different types of particles that make up matter. They're not just protons, neutrons, and electrons. And frankly, now would be a good time. You could Google that. Google elementary particles and see how many different particles physicists have found. Murray coined the term quark by taking it from James Joyce's novel Finnegan's Wake, another interesting intersection of physics and art. There are 6 types, or flavors, physicists are never great in coming up with good names, of quarks that describe their properties, and they are further classified according to their color. Again, not a real color, it's just a handy inventory management tool. They are up, down, strange, charm, top, and bottom. And they have charges that are either plus or minus 2/3 times E, where E is the elementary charge of an electron, or plus or minus 1/3 E. Before this work in the 60s, it was thought that the smallest charge on a particle was E. However, you just can't observe quarks on their own, so we'll still go with the fundamental charge as 1.6 times 10 to the minus 19th, and all objects bigger than an electron have to have charges that are integral multiples of that. A neutron, over here, this is a neutron. We have an up quark, there's a red up quark, a blue down quark, and a green down quark. That's a neutron. The study of quarks is called quantum chromodynamics. And look, here's chromo, right? We're talking about colors and stuff, so that kind of fits. And it's way, way beyond this course. But one final interesting point. The quark is subject to all four fundamental forces: electricity and magnetism, gravity, strong nuclear force, and the weak nuclear force. Just as an example, the neutron certainly is affected by these three forces, but electricity and magnetism don't touch it because it's neutral. But quarks are subject to all four forces.